Hello and welcome to video 1. The topic of our first video is basic circle vocabulary and angle properties. I'd like to remind you that as you progress through the video that the notes you have in front of you may not match exactly with the slides that you're viewing, but you do have enough information from the slides in order to complete your notes accurately and completely. Also remember that you can pause this video at any point in time in order to go back and review a particular slide or in order to complete your notes. Good luck, have fun. Circles have segments and angles associated with them that you need to be able to identify and name properly. Some of these are familiar to you, like a radius and a diameter. Remember that a radius is a segment that starts at the center of a circle and extends onto the circle. A diameter is a segment whose endpoints are both on the circle, but it passes through the center of the circle. And a chord is a segment whose endpoints are on the circle, but it does not pass through the center of the circle. Since all three of these are segments, they can be named just as we would name any other segment by using the endpoints of the segment itself. So for example, this would be segment AX, written as normal. There are also several types of angles associated with circles, the first of which is known as a central angle. Notice that the vertex of a central angle is at the center of the circle itself, and the sides of the central angle are radii of the circle. The portion of the circle that's in between the two radii, which I've highlighted for you here, is known as the intercepted arc. We name central angles just as we would name any other angle. For example, this might be referred to as angle ABC. The intercepted arc of central angle ABC is known as a minor arc. It's a minor arc because its measure is less than that of a semicircle. Let's take a look at the different types of arcs that you might find in a circle. The first one is a semicircle. A semicircle is exactly as its name implies, it's half of a circle. So this arc here is a semicircle. Notice that it's formed by a diameter, and there's the intercepted arc. There are two semicircles here. The other one would be up above. A major arc is an arc that is bigger than a semicircle. If I go ahead and name some points on this particular circle, let's call this A, B, and C, then an example of a major arc would be that of arc ACB. And we name a major arc using 3 letters, and we put the arc symbol over the top of it. So arc ACB, because it has 3 letters, it indicates it's a major arc, and we can also tell the order that it's going around the circle. So remember that a major arc has to be larger than a semicircle. As opposed to a minor arc is an arc much like arc CA over here. It's smaller than a semicircle, and you use only 2 letters to designate a minor arc. So for example, here is one minor arc, arc AB. A second minor arc here would be arc BC. Here are some circle formulas that you should already know. The area of a circle can be calculated by using the formula pi r squared, where r represents the length of the radius of the circle, and the circumference of a circle, which remember is the distance around a circle, can be calculated using the formula 2 times pi times the radius. Or, if you prefer, you can write that as pi times the diameter. It's an equivalent form of the circumference. Please note that all circles are similar. We know that they're similar because all radii in a circle are congruent, you can establish constant ratios between any two circles. Earlier I mentioned that there were several angles that could be associated with circles. We've already looked at a central angle. Remember that a central angle is an angle whose vertex is at the center of the circle. What's special about a central angle is that it helps us to also define the measure of its intercepted arc. We define the measure of its intercepted arc as being exactly the same as the measure of the central angle. So notice in this particular example, the measure of the central angle is 30 degrees. The measure of its intercepted arc is also 30 degrees. Inscribed angles are another type of angle associated with circles. We define an inscribed angle as any angle whose vertex is on the circle and whose sides are chords of the circle. The relationship between the measure of the inscribed angle and its intercepted arc is that the measure of the angle is half the measure of its intercepted arc. Again, the intercepted arc is that portion of the circle that lies in between the two sides of the angle. Notice that in the second example, one side of this angle is a chord, the other side appears to be something else. It's called a tangent. We'll study that later on in the unit. But this is still an inscribed angle because its vertex is on the circle. And if this angle has a measure of 60 degrees, then its intercepted arc, which again is the arc in between the two sides of the circle, has to be twice as big as that at 120 degrees. Now let's look at some theorems involving inscribed angles. The first theorem is that inscribed angles that intercept the same arc are congruent. If you look at our red inscribed angle and our blue inscribed angle, you can see that they both intercept the same arc, which is highlighted here in green. So if this intercepted arc had a measure of, say, 60 degrees, then because each of these inscribed angles intercepts that same arc, we would know that their measures would have to be 30 degrees. And any angles that have the same measure must be congruent. Therefore, inscribed angles that intercept the same arc have to be congruent. Our second theorem involves an angle that's inscribed in a semicircle. And an angle that's inscribed in a semicircle is a right angle. We know that the measure of a semicircle is half of a circle, so it's 180 degrees. So therefore, if this semicircle, which is the intercepted arc, is 180 degrees, then the inscribed angle must be half of that measure, which is 90 degrees. Our next slide deals with inscribed polygons. We define an inscribed polygon as being a polygon in which every vertex of the polygon lies on the circle. As you can see in the example, this is an inscribed pentagon, but you can inscribe any polygon into a circle so long as the vertices of the polygon are on the circle itself. Now we're going to investigate what happens when we inscribe a quadrilateral inside of a circle. The theorem states that the opposite angles in an inscribed quadrilateral are supplementary. Let's do a quick proof and see why this is true. To begin with, we need to draw the diagonals of this quadrilateral. So let's go ahead and draw diagonal BD, as well as diagonal AC. We know from our work with angle addition earlier in the year that the measure of a larger angle can be broken up into the sum of the measures of two smaller angles. So I'm going to allow the measure of angle ABD to be represented by Q and the measure of angle CBD to be represented by Q. Using a similar line of reasoning, I can do the same thing with ADC. I'm going to call this smaller angle a measure of X and this smaller angle a measure of angle Y. Now, if I go back up to angle ABD, that's an inscribed angle that intercepts arc AD. If I look for another inscribed angle that intercepts that same arc, I can see the angle ACD also intercepts arc AD. So that means that angle ACD must have exactly the same measure as angle ABD, which we already know is P. I can use a similar type of reasoning to discover what other angles intercept this arc. So if I use angle DBC, which has a measure of Q, it intercepts that arc. Another angle that intercepts that same arc is angle CAD, so it must also have a measure of Q. Now I want you to notice that we really have a triangle here. Whoops, let's use yellow. So we have a triangle ACD. All of the angles in a triangle have to add up to 180 degrees. So it must be true then that Q plus P plus X plus Y has to add up to 180. But we've previously established that the measure of angle ABC is equal to P plus Q. And we also know that the measure of angle ADC has to equal X plus Y. So what that means is that wherever I see a Q plus P, I can substitute in angle ABC, and wherever I see an X plus Y, I can substitute in angle ADC. So that leads me to the following conclusion, that the measure of angle ABC plus the measure of angle ADC has to equal 180 degrees. And if we go back to our diagram, angle ABC is here and angle ADC is here. Those are opposite angles of an inscribed quadrilateral. We've shown that they are supplementary. We could do the same type of proof to also prove that angle BAD and angle BCD are supplementary. This concludes our first video on circle vocabulary and angle properties. Hope you enjoyed it and that it was helpful, and we'll be practicing skills based on this information next class. Thanks for watching.